Eclipses, Astronomy and Civilization, an overview, a brief overview. I'll try to move through this in fewer than 4,000 years. Let's begin, if we can. Nothing's happening. Let's see. The night sky in antiquity. Now, raise your hand if you have ever seen the night sky. Keep them up. Where did you see the night sky? Put your hand down if you saw it in New Orleans. Put your hand down if you saw it in any major city. Put your hand down if you saw it in a town. Okay. Have you seen the night sky from the middle of nowhere on a clear night? Yeah. It is spectacular, isn't it? Yeah. It is truly spectacular. This picture doesn't do it justice. I remember as a small child at church camp in North Louisiana around 1975. At night, we were walking by the lake. My older brother says to me, "Look up." I looked up. It blew my mind. Okay, I'll never forget it. The number and brightness of stars, the clouds in the stars and things like that, the Milky Way, unbelievable. So the night sky has obviously been spoiled by light pollution for us, one of the great tragedies of the modern world. But of course, to the ancient world, it wasn't like that. It was always good. There wasn't enough light source on the ground to mess it up. Lots of stars, beautiful stars. Who lives in the night sky? Who would live there? The gods. The gods. Only divine beings could have such a spectacular dwelling place, right? So let's keep that in mind. The night sky, home of the gods. A little bit of basic astronomy. The sun is the star around which the earth revolves. The moon is a satellite of Earth. Okay. The fixed stars are true stars, visible on most nights, distant from Earth. Location and brightness vary relatively slowly. The planets, the wanderers, co-satellites along with Earth, the sun, although ancient astronomers did not know this, are often similar to true stars in appearance, but seeming to follow a path of the night sky, similar to that of the sun during the day, the sun during the day, a west to east direction. Okay, variations in visibility. The sidereal period is the amount of time in Earth's days and years it takes a planet to complete a revolution around the sun. The synodic period is the amount of time that elapses between successive identical configurations as seen from Earth, which is the only thing the ancients really knew. 5 visible planets for the Mercury, fast moving, 88 days sidereal period, synodic period. Venus, the brightest wanderer, sometimes visible during early noon. Late night, the 225 days sidereal period, 584 days synodic period. Mars, red, about a 2-year sidereal period, about a 2-year synodic period. Starting to line up there. Jupiter, the largest wanderer, 12-year sidereal period, about a 1-year synodic period. Saturn, 30-year sidereal period, about a 1-year synodic period. You might take a moment and you might compare and contrast the sidereal periods with the synodic periods. Okay, is there a question?
No, but would you speak slower and louder and will you read that again?
Planets, wanderers, co-satellites along with Earth. It's supposed to on.
Now it's on.
Now it's on.
Closer. See if that works.
This is better.
Yeah. Yes.
Although ancient astronomers. Hello. Okay, co-satellites along with Earth of the sun, although ancient astronomers did not know this, often similar to the true stars in appearance, but seeming to follow a path in the night sky, similar to that of the sun during the day, but in a west to east direction. Location, visibility, and brightness vary seasonally. The sidereal period is the amount of time in Earth's days or years it takes a planet to complete 1 revolution around the sun. The synodic period is the amount of time that elapses between 2 successive identical configurations of heavenly bodies that seem from the Earth. Mercury is the fastest moving of the wanderers with an 88-day sidereal period and 116 days. Venus is the brightest wanderer with a 25-day sidereal period and about a year and a half synodic period. Mars, the red planet, about a 2-year sidereal period, about a 2-year synodic period. Jupiter with a 12-year sidereal period and a little more than a year synodic period. Saturn with a 30-year sidereal period and about a 1-year synodic period. And as I said, I would like you to think about those numbers for a minute and contrast them and think about why those differences would be there.
Can you explain further what a synodic period is? Successive identical configurations.
Well, that would be about time for when you see, you know, the stars look one way in their relative positions. How long does it take for them to have an identical appearance in the sky? Just at that particular location. The biophysical planets, this is a terrible slide, and it only has 4 of them. Don't worry about that. They're not very good. Light pollution, you understand. Okay, the solar eclipse, also not a great resolution slide. It's rather large, but a solar eclipse is kind of simple to understand in a way. The moon is blocking the sun for a minute there. There's a point on the Earth when you really get a good solar eclipse, like a complete solar eclipse. But if you're a little further away from that point, you're going to get a partial eclipse, or maybe not be able to see it at all. Okay, I have to go to it. A lunar eclipse, of course, is sort of the opposite. That's when the sun, rather than the Earth, is blocking the sun's light on the moon. How is it different from a new moon? In order to have a true lunar eclipse, that has to happen when the moon's orbital plane happens to intersect the ecliptic plane right there, when the moon and the Earth and the sun are in a direct line. Okay, the moon's orbital plane is a little sort of tilted there, okay, compared to the Earth's rotational axis. Okay, causes all kinds of problems. You can see it already from here. The solar system is a little messy in some ways. Okay. Let's talk about the Babylonians. Okay, early astronomers. Just for fun, I have pictures. Nana, the moon god, not goddess, by the way, god. You see a moon there. Marduk, the celestial sovereign, associated with Jupiter. Just for fun. So nice pictures. Let's get into the nitty-gritty. Babylon, okay, a collection of successive states or civilizations: Sumerians, Babylonians, Assyrians, Neo-Babylonians, Persians, and Seleucids. Of course, Alexander the Great's generals who inherited his empire. We've got a time period from 4000 BC or BCE up to about 63 BCE with a continuous language and number system, or let's not say continuous, but a readable language and number system. In other words, the oldest cuneiform could be read by people during this period here, Alexander the Great's generals, by astronomers, scholars, and learned people. So you have a kind of a continuum for a long period of time here. Okay. That big data on the Euphrates. Okay, the Babylonians were the great record keepers of the ancient astronomy world. Okay, the cuneiform, of course, as we know, was translated in the 19th century with Rawlinson and others. And we have a collection of sort of standard, if you will, Babylonian astronomical tables. The astrolabes, very old, from 1800 to 1100 BC. Just a record of data, right? Rising and falling of stars, things like that, appearance and disappearance of planets, length of the day, lunar visibility. They're not complete anymore, but some of those are in the British Museum. You can actually go see that stone tablet if you want to, okay, in London. Okay. The Enuma and New Enlil, dating about 1800 BC, a collection of omens derived from eclipses of the moon, the omen mounds, okay? Found on 70 stone tablets from Ashurbanipal's library at Nineveh, preserved till the end of the Seleucid period. They exist now only in translation. The reports, 7th century documents of the Assyrian royal court about what happened with the omena. So this is a kind of early proto-science, okay? It's not true science, but the ancients weren't stupid. So if they had an omen or a prediction, when the moon is red, an army will be defeated in battle. They'd write it down. Next time the moon was red, they'd check, was an army defeated in battle or not, okay? So that's the sort of record keeping that they did there. The astronomical diaries, a collection of observations and divinations from the 7th century BC to the 1st century BC. They include tabulations of lunar, planetary, and meteorological data, along with economic and political data, such as the level of the Euphrates, the price of grain, etc. Isn't that fascinating? What does the setting of Venus have to do with the price of grain? Probably nothing, but they weren't sure. So they included that data. Again, it seems a sort of proto science, and there's kind of data science, if you will, of the ancient world. The Babylonians had a sophisticated lunar calendar, 235 synodic lunar months, each lasting 295 days, transpired over a roughly 3-year cycle. So they basically had a 20-year calendar in a sense, subdivided into 12-month years and 7 13-month years. They were able to predict lunar eclipses. By the end of the Babylonian period, the Seleucid period, they were able to predict solar eclipses with about 60% accuracy, about 20%, that's a typo. It's supposed to say these wrong predictions relate to phenomena observable from other parts of the Earth. There was an eclipse when they thought they would be, but they just couldn't see it. Astrology, as we know it today, is around 400 BC. Now, as we're mentioning here, this was accomplished using not only various forms of cuneiform, about 500 symbols in the cuneiform writing system, but also the Babylonian mathematical system, a base 60 number system encompassing multiplication, division, tabulated power functions, roots, and reciprocals. Sure. One moment here. Of gods, the astronomers, while technically not members of the priesthood, were members of the elite under commercial communication.
Y'all can get y'all snacks. You can get your snacks. You can get your snack, Amon.
Positions of stars, the time of eclipses, positions of the planets, you're able to predict their future appearance. Even if you don't have any explanation for why they are where they seem to be, when they seem to be. Some changes people are pushing that the Babylonians did have a kind of what they call geometric astronomy, but
Away with that cake. Come back.
just on a couple more Babylonian deities here. If you're as familiar with goddess of fertility, but Venus, Shamash, god of justice, identified with the sun. So notice here, Venus has a little Venus in the upper left. The sun has a sun and a moon. I'm going to move quickly here because I don't want to cut too much into Greg's time. Just mention a few things here. Difficulties for the ancient astronomers. The moon is a problem. The moon is a big problem because it looks in the sky to be about the same size as the sun. But, and you're learning before lunch, the moon is actually smaller than the sun. Okay, quite a bit.
Okay, it moves in the night sky, much as the sun moves in the day. It influences tides, just as the sun governs agricultural fertility with its monthly cycles and lunar cycles, which has to do with human fertility, obviously. So it's natural to sort of elevate the importance of the moon in some ways to be kind of like the sun. Okay. Planetary motion is seen from the Earth because Earth and the other planets are all around the sun at speeds. Mars, Jupiter, and Saturn appear to reverse direction for a part of the year with Earth's surface. Retrograde motion that many of you may be familiar with. Very problematic for ancient astronomers to come up with a coherent physical model to sort this out. Relative magnitude of celestial distances versus apparent size of celestial objects. The closest visible planet to Earth, Venus, is about 40 million kilometers away. And its closest, the nearest fixed star, Proxima Centauri, the nearest Centaur, is about 40 trillion kilometers away, or 1 million times further away. Yet, seen in the night sky, the planets and self-fixed stars seem similar in size. They don't seem millions of size orders different. But of course, circular movements, the visible movements of the sun and moon, just circular orbits. Circles are perfect geometric objects with an intrinsic appeal. They just don't actually play the role that the ancients thought they did in planetary motion. I'm going to move very quickly and just summarize a few other things now. Okay, Greek astronomy. There's ancient Greece, talking about 800 BC to about 140 BC. Here are some Greek gods: Mercury, Venus, Mars, Jupiter, and Saturn. Now, there's a little speech balloon you can't see here. Mercury is speaking to Venus, and he's saying, "Hey, well, come take a ride on the sheep." Venus is saying, and Saturn, of course, with his side pond, is saying, "Have fun." Let's mention all this. Why do I mention all this? Because, and I just can't go through everything. I can't go through both in and rare for ground. The physical explanations for planetary motion in a way that the Babylonians did not. No, why did the Greeks try to explain what Jupiter or Mars would do in a different way? It may have something to do with the Greek gods and European religion. Okay. I mean, it's a religion, which pushed by devils, right? It's got Socrates. Please put to death the discouraging belief in the Olympian religion. And Socrates' point was, you know, if you think about Greek mythology, he's like, worship these guys? I mean, are you kidding? I wouldn't even let them into my house. You know what I mean? So maybe they enabled the Greeks to somehow desacralize planets. And also, this identification of Olympian deities with planets is an overlay of Babylonian civilization. Okay. Those guys actually originally lived on Mount Olympus. They weren't planets, they were sort of identified with planets. When like sort of they labeled the planets, named the planets after the gods. So a different thing. Greeks, as we know, developed various cosmological theories, various explanations for the shape of the universe, the shape of the solar system, the motion of the planets. And Aristarchus posed the sun-centered universe, which is wrong, for the time, estimating sizes and distances, Earth to the moon and sun. But here's a problem with the Greeks who had, if you assume that everything is going around the sun, if all is going around the sun, distant stars appear to change position more quickly than they do if they were pretty close. If the fixed stars were around where the water planets are, you see a bigger change with the Earth going around the sun. And again, that's an astronomical distance magnitude problem. The ancient Greeks and other ancient astronomers could possibly know how far away the fixed stars are. So it doesn't really matter if Earth goes around the sun much of how they look. Certainly not with the technology of which is known of the naked eye that they had. So Greeks eventually settled on this model, sort of ptolemaic model, in which everything, the planets and the sun go around the Earth, and retrograde motion is explained through little epicycles, little cycles within cycles. And Ptolemy and others invented very sophisticated mathematics and geometry to explain this. This is important in the history of science because their detailed mathematics and their ability to predict phenomena were based on a fixed numbers. Okay, and this is something that can happen. You can complexify models to a very simplification. Okay, it's what we call the green shirt phenomenon. I got an entry. Next time, I'm going to try to get an A again. Getting a green shirt when I took the test last time. So I'll wear a green shirt next time. My astronomy test. I was wearing a green shirt. Oh, I have to wear the blue tennis shoes and the green shirt. Still doesn't work. I have to have the green shirt, the blue tennis shoes, and borrow my sister's car to get to you and everything. And so on. So you can complex numbers through falsification. That's right. There's science at the end of the day. We need some stats and right. We can measurement and observation. Okay. Mathematical models are not enough. I'm going to get out now, but I'm just going to have a look on quick. The new world, Mayan astronomy, the Earth, the 9-2. Okay. I have a calendar actually here is that you circle inward and you see that face right there. That's April 14th, right there in the morning. That's supposed to get a laugh. No, everything. And we're in Mesoamerica, a sophisticated civilization. Okay. Nice architecture, like the Babylonians. We have Mayan architecture today to the general way mentioned it. We don't have Mayan, most of it was destroyed by Diego de Lapa. We have a policies though. This is a Mayan. This is the thing. It's touristic text. This is Maya. We use writing and some mathematics. Let's have Mayan here. A very natural number system based 20. The one have shoes, but they had based 20 mathematics. And those are numbers. Yes, that we can read. Mayan architecture or palace architecture shows almost evidence to bring evidence astronomical functionality. These ground plans of these palaces, let us claim them, palaces or temples, to moments. And see the architecture. Something they did not have to bend it out. Strange hangings of buildings here, but what is it? Steps and everything. It's reaching so many lines of sight, like the visible planets, and line like situation one of the dimensions. That is strong.
They can
Strong.
switch with him for the HDMI.
Mayan calendar, so
You want me to run your stuff?
also have 360 days. Yes, they simply down. Yeah, which that means there can be residency. The lizard, it's a lunar and soon. Revolutions and so on. Fly whatever to eclipses. 50. I'm obsessed with chronological cycles, often involving death and rebirth, that are individuals of the cosmos. They felt the need for intervals of time to divide evenly into one another or multiply into one another. But Gaia didn't have fractions. So they had to get least common multiples of ever larger sets of numbers to get these sacred cycles to sort of fit together. And they came up with these sacred numbers. 1,366,500. 10,526 pregnancy days, 10,700 years, and synodic condition years. It's so fun. Okay, I'm out. That's it. Thank you.
Equipment technology, they're flying around the blood bank that's on the UNO campus. Coming over all right?
Yeah.
Okay, good. I'm going to do a little bit of show and tell. So I have a table here full of goodies. And let's do a very, very short introduction. If you would advance my slide, please. Right button. Down button. Whoa, what's going on? Oh, I know what's going on. There we go. So this is almost a slide. The screen of death. Tell you what, I've got lots of pretty pictures, but I've also got some toys. One of the things I wanted to show you and talk about, this is really the important stuff, is how you safely observe a solar eclipse. And there's one huge, huge, huge rule. That is, don't look at it. If you look at the sun, first place, if you just stare at the sun naked eye, you will burn your eyeballs out. Because you're focusing the heat of the sun on your retina. And it's there we go. Now, can we figure out how to advance and go back? Okay. There we go. All right. So you want a pair of eclipse glasses. Nothing else will do except number 14 welder's glass if you happen to have a welding helmet, and it has to be number 14 or better, or it won't work, because you can't use anything that just makes the sun dimmer, because the problem is the UV light, which is what burns your eyeballs out. And if you don't have eclipse glasses, you're not really screening out the UV light. So just don't. And the way you use, first place, you check your eclipse glasses. If you can see anything through them, throw them away. Because they block out so much of the light that you really can't see a thing except the sun. And then face the sun, put them on over your glasses, and then look up. Uh-oh, I can see a light. No, these are fun. So the eclipse glasses are certified. There's an ISO standard, which I'll show you in a moment. First, let me point out why it is that seeing a total solar eclipse is rare. And that is the moon's shadow comes to a point right there for the umbra or darkest part of the moon shadow, which is where the entire sun is shielded by the moon. Since the sun and the moon are almost the same size on the sky, although the sun is 400 times bigger than the moon, it's also 400 times farther away. Sheer coincidence. As the moon moves farther and farther away, in a billion years, we won't have this kind of eclipse anymore. So, make sure you go look at it quick before the next billion years pass. Advance, next slide. So that tip is what makes a solar eclipse rare, because you've got to be inside the track of that tip in order to see one. And we had one come through in August 2017. And this one is coming right up here, and the next good one is going to be 2045. So I have in my life missed 2 opportunities to drive someplace to see a total solar eclipse. I'm getting old. I'm not going to miss a third, unless weather gets me, of course, which can always happen. So you want to use eclipse glasses. That's the best way. Get them early if you can, because they will not be, they'll be sold out during the eclipse. But you got to drive to Texas to see the eclipse. I'm going. I'm not missing this opportunity. And I have a niece that lives in Dallas. So, taking my entire family, we're going to load up her house and wait for the eclipse. All right, these aren't very expensive. They cost a couple of bucks. You can actually get them in Lowe's, although it's probably better to order from Amazon. And you make sure you get a good kind. Next slide, please. Let's go ahead. Let's get this. You get partial solar eclipses, annular solar eclipses that we just had last year, and total. And what we're looking for is totality, because you get to see the sun's atmosphere, the corona and chromosphere, which you can't see ordinarily. It's there, but it's washed out by the bright disk of the sun. Next slide. So, safe viewing. You can use eclipse glasses. I wouldn't stare at the sun for too long, even through eclipse glasses, because, I'm conservative. I only have 2 eyes. And if I burn them out, I'll have none. Pinhole cameras, which I'm going to show you how to do, and a telescope if you've got someone that knows what they're doing. So let's go on to the next slide. Unsafe viewing of the sun. Stare at the sun, with the eye, or through flash photographic film or floppy disk. I don't know how that works. Forget that. Smoke glass, any sling glasses. Do not do that. You got to have something specially made for solar observing, or you'll burn your eyeballs out. Particularly, never, ever, ever even glance at the sun through an ordinary pair of binoculars or telescope or magnifying glass or anything that magnifies it, because then you can burn your eyeballs out before you can blink. If it starts to hurt, it's too late. if you keep staring at it, as some teenagers found out a couple of decades ago, idiot teenagers, it will quit hurting after a while because it's burned your eyeballs out. You no longer have any nerves to hurt. Yeah. No. Right. So anytime that any part of the sun's disk is visible, you need eclipse glasses or other eye protection. However, during totality, take off the eclipse glasses because the sun's completely covered. And it's going to be almost 4.5 minutes through most of Texas. Wow, I'm looking forward to it. It will get dark. What I'm a little worried about streetlights coming on and spoiling the view. You'll be able to see the chromosphere and corona of the sun. Never seen that. Love it. I want to. When the sun starts to emerge, or rather when the moon starts to move off the disk, put on your sunglasses again. Eclipse glasses.
I have a question.
Yes, sir.
So when it's total, can you use your binoculars at that point?
Well, yeah. Let's say something, but be very careful because you don't want to still be looking at it when it comes out.
And if it's only halfway covered, you better keep you leave your glasses.
Right. If you can see any part of the sun, and usually there's a couple of little bright spots called Bailey's beads that come out first, and that says, quit looking now. All right, you should be able to tell. I don't know, I've never seen one. You need eclipse glasses that meet the ISO 12312-2 compliance. And you prefer to have eclipse glasses bought from someplace or some brand that has been investigated and approved by the American Astronomical Society. And yeah, I've given a reference here that you can go to. It's a long list. So if you got both of those, oh, good. And it's actually printed on these eclipse glasses. And then they should last a fairly long time if they're made to this standard. All right, next slide. But one of the easiest things to do, if you don't happen to have eclipse glasses, or even if you do, is to make a pinhole camera for yourself. So I brought along pinhole camera fixings. First, you need a box. If almost any kind of box will do, big, small, medium, not too small, because you'd like to have at least about 1 foot of space. A large cereal box will work. A concatenation of tubes. Then you need some duct tape. I'm using blue tape instead, but you know, it works. And of course, a pair of scissors. A piece of paper, I've already cut this down. Some aluminum foil. And a sewing kit. Well, you don't really need the sewing kit. But you need a pin. And so what I'm going to do, one more thing. A knife. Because I'm going to stab this box like this. And just cut a moderate sized hole. Now, instructions say, use a quarter to get the hole the right size, and it does not matter. You want a hole. Yay! And then you take some tin foil and some duct tape. Because what you're going to do is tear off a little piece of tin foil. Heavy duty is good, not necessary. And tape it on with some, this is blue painter's tape, but it doesn't matter as long as it sticks. So I'm going to tape it on.
Just tape over the hole.
Yes, ma'am.
You can't see.
I'll turn it up so you can see it just a moment. Okay. Now it's time for the sewing kit. And I use the sewing kit because a sewing pin is just about the right size. A push pin, it actually, there is a right size depending on your length. And so a sewing pin is actually a little bit small. One thing you can do is make holes of various sizes and just experiment with it and play with it. Of course, you can test it out before the eclipse. I do not want to spill all of my pins all over. So you do this amazing thing is you put a hole in it. A pinhole. Amazing. Oh, I didn't get it very round.
Are you using a straight pin or a sewing needle?
A straight pin. Sewing needles, you have to worry. You don't want it too big, you don't want it too small. So experimentation is in order. I was actually first did this with a somewhat smaller box for which I needed a 0.8 millimeter pinhole. And so this kind of pin was about right. All right. Next step is you take your white piece of paper and put it on the side inside opposite the pinhole. Take it down. And that's your screen. Well, you're done. If you're going to leave the box partially open, and what you would do is if the sun's over there, you hold it up like this to project a pinhole image of the sun onto the screen. You can be a little bit fancier by making another hole for you to look through. And I tend to like doing that. It can even be in the side of the box, like here. And that way you can close up the box, have it a little bit darker, and still look through here at the sun. Okay, so there's the hole that you look through. If you have a larger box, you just put it over your head. One of the problems with this is the sun is bright. And so it can actually wash out the image from the pinhole camera. And you will indeed see the eclipse. Right? It's fun. That's easy. You can look up instructions all over everywhere. You can do it any way you want. Next slide. You can use a large cereal box. Pringles can. I think that's interesting. Or take together some paper towel dowels, put tinfoil on one end with a pinhole in it, put out a little bit from the end for the screen, and here you can see a little image of the sun. Experiment ahead of time. You'll just get a circle, but that's all right. Next slide. And if you don't want to go through all of that effort, go find a tree. The leaves of a tree make wonderful pinholes. And there you can see an image of a partially eclipsed sun. Just, hundreds of them under a tree. I actually discovered that accidentally some years ago when we had a partial solar eclipse. I walked under a tree and just stopped and froze and said, no. Or just a piece of cardboard with a hole in it. Or you can even just take your hand, make a small hole, hold it up to project an image. Or this one I've never seen, kind of cross your fingers and adjust the size of the hole until you get good images. So it's not hard. Next slide. But if you want to be fancier, you can, and you have a telescope but don't have a solar filter, you can do projection very easily. And one of the things about doing the projection is that the sunlight coming around the camera can wash out the image. So if you have some kind of a color or shade, it will help a lot. Problem is finding the sun without looking. But there's a trick. just look at the shadow, make the shadow of the telescope as small as possible. And then just move it around a little bit until you see that nice bright image of the sun. And it's wonderful. Binoculars, make sure, by the way, if you've got a finer scope, take it off for covering. That's what this shadow here is, it's a finer scope. If you're using binoculars, cap one side of it. Because you don't want to accidentally have look through that, or stick your hand under it and have burn your hand. Because you know you can set something on fire real easy with this. Okay, next slide. And if you have someone who knows what they're doing, I recommend you actually have someone who knows what you're doing. And you've got about $100, you can buy a solar filter to fit on the front of your telescope. And this is specially made for solar viewing. You see, I've got some blue tape on it because whenever I use this, I tape it on the end of the telescope so I can make sure it doesn't fall off. I also had to put in some cardboard shims for it to fit tightly. Then you find the sun, you can actually look through the telescope then at the sun, but make sure it is a designed for solar filter. And if you want to try that, you got to order it in advance. Let's see. For our last eclipse, I found a pair of solar binoculars. Okay. This is specially made for looking at the sun. I was afraid to use them in a crowd because somebody will say, oh, look, he's looking through his binoculars. They get their binoculars and burn their eyeballs out. But it says on here, which is too small to read, solar safe. So these incorporate the filters for looking at the sun. And that is the big, big message, is make sure. Now, finally, you want to take a picture? Of course you do. Don't take your cell phone and point it at the sun. You'll burn your camera out. Better than burning your eyes out. Of course, if you've got an old-fashioned SLR camera that directs the photo straight through to your eye, you can still burn your eyes out. But if you get a telescopic setup like that, it's actually not terribly hard to just kind of position your cell phone in front of the eyepiece in order to get a decent picture. It takes some experimentation. It's a little easier if you buy an adapter like this. And this fits on. Okay, so your cell phone fits on there. You can move it left and right. And this clamps onto the eyepiece of your telescope to hold it steadier. And it actually does work. Can we get the next slide, please? So I have a picture of that. Or you can take one of these glasses, hold it in front, and do that. Now, one problem is getting a good exposure. So I actually bought a little app that came with these solar filters here and a little Velcro piece that sticks on my telescope so I can stick it like that and don't have to hold it in order to cover the telescope camera lens. And then you got to figure out which one of all those little spots is actually the lens. I mean, they now have 4 of them or more. And that works. The app also has some special controls for manually setting the exposure and the magnification on your cell phone. So a little cell phone app can help get you better images. Next slide, please. And oh, be safe. The primary thing is be safe, right? If you're not sure if it's safe, don't do it. Okay. Even using a telescope, strongly recommend you get somebody who knows what they're doing. Any setup you want, go out and practice while the sun is not eclipsed. Make sure you can get it right. And I don't know if you're going to publish these slides or make them available anywhere, because I've got some references here that online you can find good information about how to look at an eclipse. And my favorite is the last one, which is American Astronomical Society, of which I am a member these last 40 years or so. Thank you. Let's have 2 minutes over. Do we have, should I take questions?
Y'all have questions?
Briefly, yes, sir.
You mentioned in Texas, it might be a 4-minute totality of blackout. Is there a theoretical maximum? Could it be 10 minutes somewhere?
I think the theoretical maximum is around 5.5 minutes. So we're pushing close to the maximum. So that's a good one. I mean, it can be all the way down to 0. So 4.5 minutes is good. I'm looking forward to it.
I read that Austin was the center of the path.
Well, the center track stretches from Mexico up through Texas and into the Tennessee, Kentucky, and out the East Coast.
So in Dallas, are you gonna see the total eclipse?
Absolutely.
Good.
Look up, be careful. Travis County around Austin has already declared a state of emergency because they're worried about it. Don't leave it to the last minute. My niece lives in the totality track, so I'm good. Yes, sir.
What will we see in New Orleans?
The commercial.
Park.
Yeah. And
What percentage?
I think it's about 85%.
yeah, about 85%. Now, Laura is going to have a little
Yeah, well,
feeling because me and everybody else I know in the physics club, all the students are going to Texas. So we got nobody left to do this.
yeah, we'll have glasses, got them from Thousand Oaks, it's certified, say, so we're in good shape there, first come, first served at the day of. Shreveport will have 97% coverage too, so if you wanna go 5 hours, 6
Yeah,
hours.
it's going to be. I didn't look up the time now. In Dallas, it's 1:40 p.m. I think in Austin it's 1:30, so it's going to be like right around there here.
It's like 12:30 here, somewhere, I think I said it.
Okay,
I have it in my head, it's around.
for max, I mean, the whole thing lasts for
Yeah.
a couple hours. Yes, ma'am.
Follow up on that comment. Will that be posted somewhere on your webpage or?
The library's webpage? Yes, yes, we have a little carousel of images and we put things up there, so when we get a little closer, I didn't wanna get people wanna ask for them in advance and because we have a limited number, we really do wanna distribute them the day of, so people hang out, appreciate it with us, not just take them somewhere and then forget about it, right?
I would be remiss if I didn't put in a plug. We're going to have an open house at the UNO Observatory on March 22nd. Weather permitting, if it's cloudy, we won't do it. Can't see stars. We're going to take a look at Jupiter, the moon, and possibly the Orion Nebula. And the Physics Club has eclipse glasses that they will sell you because they had to buy them. It's in the Science Building, 3rd floor, and it starts more or less at dark, which is going to be around 7:30, and run for a couple of hours. And if you've never been up there to the UNO Observatory, oh, it's fun. Here, you have a flyer. Okay, other questions, please? And I will put this over, I'll put this on the table and y'all can grab them all. Yes.
Yeah, if Laura or you could hold back up that picture that showed where the paths are. Yeah.
Oh dear, no, well, it's gone now.
Because, it shows that swath that you were talking
Yeah.
about. How long is really the eclipse and it tracks across the United States?
Oh, as the Earth rotates and the moon moves, you get a track that covers several thousand miles. All right, and it varies in the time, how long you see totality, if you see totality, and of course where it goes. And the tracks look kind of funny sometimes because of the combination of motions. One good place to go besides the American Astronomical Society site would be also there's a site called Time and Date. That's, I think it's somewhere on those slides too. That is very good for seeing sunrise, sunset time, moonrise, moonsets, and planets, anything else you want to, yes, sir.
So clarify, please, if we were to travel to Texas, what day would we expect to see?
April 8th.
Wait, that's a Monday?
Monday.
That's a Monday.
Yep.
I would not try and drive there on Monday. And it's real hard to find a place to stay.
Yeah.
Unless you've got some thousands of dollars. Even campsites have prices going up into the thousands of dollars. But you can stay someplace close to the track. You know, and then go in on Sunday. I have no idea how bad the traffic will be. So I'm glad that I'll be spending the night within the totality track. Yes, sir.
Oh, is there a website where we can get a good map that shows the trajectory of the?
Yes, ma'am. There are many websites. So if you just do a Google search on 2024 solar eclipse.
And you can even put in your location to help give you an idea of the time. So you know when it will start and when it will finish, because every location will have a slightly different time and a slightly different length because of the position of the earth.
One of my references also gives weather predictions, which is, kind of global percentage chance of having clear weather.
What does it say for Dallas?
Pretty good. But not 100%. It could be rainy. With my luck, it'll be snowing.
Wildfire.
Oh, well.
Well, we feel I need to wrap this up. One more question, and then
It's more of a comment. At the last eclipse, I found it very helpful to get a white poster board and put it on the ground. That way you can see those snake shadows that appear right before the eclipse. And also if you have a colander and hold it above, you see the dips of those shadows.
Yeah, I saw one picture where somebody had like a stirring spoon with all the little
Yeah.
holes in it. So, and the sharpness depends on the size of the hole and how far away you are from the screen. So you just experiment. You can even take a piece of cardboard and make different size holes in it, in order to see the difference. You experiment. Don't be afraid of anything except staring at the sun.
And the library quad has an awesome array of oak trees, so if you do come to campus and to watch the solar eclipse, go under a tree and check out the ground, see all the crescents all over the place. So thank you, Greg, and I think Joel had to leave, so one of the things we like to give our guest speakers is a umbrella.
I think I'll need that later today. Thank you. Thanks a lot for having me. And for having this whole series.
Very informative. We appreciate your time. Also,